Okay, today we're going to look at the Newton's second law. So his first law was the law of inertia, and basically what we're doing is we're looking at what happens when there is no external force. So if an object is at rest with no external force, it's going to stay at rest. And if an object is in motion, it's going to continue in motion at a constant velocity if there's no other external force acting on it as well. Today, Newton's second law now is sort of the same, except it goes one step further and it's asking, okay, what's going to happen when there is an external force? So the way Newton wrote the law, we'll go through pieces again to make sure we understand what it means. So the first part says when we have an external unbalanced force, that's what we're talking about. So now we have something it doesn't matter if it's at rest or if it's moving. If we're applying an unbalanced force, that's going to cause it to accelerate, and it's going to happen in the same direction as whatever direction the unbalanced force is. So which makes sense, it's kind of obvious, right? If you had a box and one person pulls on it one way at 100 newtons and the other person pulls on it the other way with 80 newtons, we now have an unbalanced force. So that means it's going to accelerate because we'd have a net force of 20 going to the right, right? So we'd have a positive 20 net force. So that means because it's moving to the right, our acceleration then is also going to be to the right. So that's the first part of the sentence. And then the second part that Newton came up with, that is probably the key to Newton's second law, is he calculated that the acceleration is going to vary directly as the force. So that means the larger the force, the larger the acceleration, which makes sense, right? If you push harder on something, it's going to move it faster, it's going to accelerate more. And the second part says inversely as the mass. So what that means is as your mass gets bigger and bigger, the acceleration is going to get smaller and smaller, which also makes sense because right, if you have something really heavy, it's going to be hard to move it. So as it gets bigger and bigger, the acceleration is going to get smaller and smaller. So what Newton figured out is because those things are directly related, and he came up with his Newton's second law formula, which is probably one of the most famous in all of physics. And we actually do it, I'm going to rate it first the way Newton did it. He was actually trying to calculate the acceleration. So the way Newton's formula is written here, it says the acceleration varies directly as the force. And we're talking about net force because there's a whole bunch of different forces acting on it. So it's going to be the net force, and then inversely would be the bottom part, would be mass. So Newton's second formula is actually written like that. Acceleration equals force divided by mass. Okay? Quite often what we're going to do is we're going to use it the other way around. We're going to go force equals mass times acceleration. So those two formulas you're going to use often when we're dealing with any of these questions that involve force. So Newton's second law, unbalanced forces, and then we can actually calculate the acceleration or the force depending on whatever information we're given. Okay, so we'll do a couple easy examples first just to kind of see how these two basic formulas work. So the first one is we want to calculate the force acting on an object that weighs 5.5 kilograms, and that object's going to be accelerating at 3.5 meters. So it's a pretty easy question, and remember, we're always just dealing with net force. We don't really care if there's 10 people pulling on it. We just want to know what the balanced final resultant force is. So in this case, our formula we want to use is net force equals mass times acceleration. So we just go 5.5 kilograms, and we're going to times that by 3.5 meters per second squared. So if you do that on your calculator, we get an answer of 19.25. And our units are kilograms, meters per second squared, right? In force, we're combining meters and seconds squared like we did in the previous unit, but now we're adding a mass to it. And our standard units for mass will be kilograms. So any question you get that aren't in kilograms, change it to kilograms. And just to save things, save a little bit of time, what we've done over the years to honor Newton, because he came up with this, is we called 1 kilogram meters per second squared a Newton. So the net force acting on this, rounded to 2 sig digs, would be 19 newtons. Okay, so that one's pretty easy. So let's do one more easy one. So now let's suppose we say determine the acceleration on a 2,000 kilogram car if 2,500 newtons of force, so 2,500 newtons of force acts on it, or basically, so what we're talking about is you're driving your car, you're going to hammer on the gas, and it's going to give you an extra 2,500 newtons of force to the tires. So I'll just leave it at that. We don't need to get too specific in rating the question. So we'll just say 2,500 kilograms of force. Actually, let's even call it negative. So that means in this case we're going to be hitting the brakes. Okay? So in this case we want acceleration. So we'll just use acceleration equals force divided by mass. So that'll be negative 2,500 divided by 2,000. So an easy calculation, and we get negative 1.25. We round it to, the question was 4 digits, so we can leave it as 3, or we can even write it as 1.250 if we want, and that would be meters per second squared. Okay, so if the force is negative, then obviously the acceleration is going to be negative as well. In this case, the car is slowing down. Okay, let's do a few harder examples now. So quite often you're going to get questions that you're going to have to draw free body diagrams, calculate net force, and then from there you'll be able to find things like acceleration. So what we want to do is, in this case, let's suppose we have a 50 kilogram object and we're going to hang it from a rope. So we have a tension on the rope. Let's suppose we're going to lift upwards on the rope at 600 newtons, and then the only other force acting on it would be gravity going downwards. So the question is, what is the acceleration of the rope? So common sense is going to be, if we apply more force to lift it up, it's going to accelerate upwards. If we have less force than gravity, it's going to accelerate downwards. But all that should be taken care of in the math once you do the net force calculations. So most of the tricks to these questions are going to be to actually figure out the net force. So in this case, we need to figure out the net force. We got 600 going up. We're going to have to calculate gravity going down. And remember, gravity is just mass times 9.81. So we go 50 times 9.81, and that gives us an answer of 490.5. Okay, so we have 490.5 newtons going down, 600 newtons going up. So our net force, remember, is always just adding the two vectors, or all the vectors together. So in this case we have 600, and we're going to add on negative 490 because it's going downwards. Or you could think of it as just 600 minus 490, whatever, it gives you the same thing. So we have 600 minus 490.5 would give us a net force of 109.5. Okay, now that we know the net force, we can easily calculate the acceleration, because it would just be the net force divided by mass. So we'd have 109.5 divided by the 50 kilogram mass, and we get an answer of 2.19 meters per second squared. And in this case, our sig digs would be 2 digits, so we'd round it off to 2.2. Okay, so pretty easy question. The trick, really, the work in this question is calculating the net force first, and then finding out the acceleration. So let's just suppose we change this question. So let's suppose instead of being 600, let's suppose the question, the net force now changed to 400. So if all of a sudden our force of tension is 400, how is that going to change the question? Well, our net force will be, instead we're going to have 400 plus negative 490.5. So now our net force is going to be negative 90.5. So that means our acceleration will be negative 90.5 divided by 50, which will equal negative 1.8 if we round it to 2 sig digs. So like I said earlier, you don't have to worry so much about the gravity being negative so much anymore and all that kind of thing. Just basically calculate your forces and then let directions sort of sort itself out. So in this case, we have 490 going downwards. That's bigger than the 400 going upwards. So obviously we're going to get a negative answer for our acceleration because it's going to move downwards. So pretty easy calculations. We're just sort of the key is finding the net force, and then after that, just dividing force divided by mass in order to get the acceleration. Okay, the next couple examples we're going to look at, let's do another one that's a little bit harder, is what happens when objects are tied together or hooked together. So let's suppose we have a 20 kilogram box, and it's going to be hooked to a 10 kilogram box, and we're going to pull the two that are hooked together. So we'll have our applied force going to the right, and let's suppose we got a friction that's going to work against us. We're going to have a force of friction going to the left, and let's suppose it is, let's suppose we have a force of friction of 100 newtons. So now the question is saying, if we accelerate the boxes at, let's say, 2.5 meters per second squared, what is our force applied? Okay, so in this case, we've got the two boxes hooked together. We're going to pull them, drag them like a train. We have friction slowing us down. The question is, how much force do we have to apply in order to get those two boxes to move? So the key thing you want to do with these kind of questions when they're hooked together is treat them as one object, because they're tied together. It really makes no difference whether we pulled the two boxes hooked together at 20 and a 10, or we could just pull one box together at 30. Okay, and then we think about our forces acting on that. We got our applied force going one way, we got our friction going the other way, but remember we also have gravity going downwards, because it's sitting on a table or whatever. So, but then because it's on a table, we're going to have a normal force going upwards. So you can see all of these forces, they're acting in all different directions, but we can ignore the normal and the gravity because those are going to both be the same. Whatever the force of gravity is going downwards, the normal is going to push upwards. So the net force will be 0. Horizontally, though, we won't get a net force. We know our friction was 100. And if you're accelerating it, that means we have to be bigger than 100 going to the right. Otherwise, it wouldn't accelerate. So we can ignore the up and down motion. We just want to worry about the horizontal. So in this case, if we know that it was accelerating, that means we can actually calculate the net force. So our net force will be the mass, which is 30 kilograms, times the acceleration of 2.5. So that gives us a net force of 75 newtons. So that means if we had a net force of 75 newtons, that means we can then kind of use common sense to say, well, in order to get a net force of 75, we've had to pull it at 175, because the 175 minus 100 would give us the 75. Or, if you want, you can just use the formula. So our net force will be the force that we apply plus friction. We know the net force was 75 newtons. We're looking for the applied force, and we know that friction was negative 100 because it was going in the opposite direction. So then we could just basically do some simple math. To solve for force applied, we'd have 75 plus 100. We'd have to cancel the 100 on both sides. So we'd have 175 newtons being our force applied. And because we didn't have to worry about the up and down motion, that's it. We just have the two forces, friction going one way at 100, our applied forces at 175. Therefore, we get a net force of 75, and if you go 75 divided by 30, that would give us our acceleration of 2.5 that we calculated. So the key thing with this question is just sort of treat them as one object instead of two separate boxes, and that makes the question quite a bit easier. One more we're going to look at is a little bit more difficult because it's still two boxes being tied together. The difference is now they're going to be hanging over a pulley instead of being flat on the floor. So let's suppose we have a 10 kilogram box hanging there, and then we've got a 15 kilogram box hanging on the other side of the pulley. Okay, so we've got no other forces acting in play. We just have these two boxes hanging against each other over the pulley. We know, sort of using common sense, that the heavier one's going to go down and the lighter one goes up. So we know it's going to end up getting some sort of motion, sort of like that. So the question is, what is the acceleration. We want to find the acceleration of the box, or boxes. Okay? So the trick to this one is, first of all, we got to ask ourselves, what are our net forces? So the only forces we have acting on these boxes are the force of gravity. So before we won't worry about what's going to happen in terms of the direction, let's actually just think about our forces to start with. So we got force of gravity acting on this one, and that'll be 15 times 9.81, which is 147.15. And then we're also going to have the force of gravity acting on this one, which will be 10 times 9.81, which will be 98.1 newtons. Okay, so we have our two forces going down, and that's it. So our net force, just using common sense, will then be 147 minus the 98, right? Because if they're counteracting each other, our net force then would be the difference. It'll be about 49 newtons roughly. What you want to do to answer these questions, though, is think about what's actually happening. And if you think about it, the pulley really isn't doing anything other than just changing directions. So that would be the same thing as if I just said the one box is getting pulled to the right. Let me fix this up a little bit. So the pulley, if you just sort of imagine the pulley is just changing directions, it's sort of like a tug-of-war in this case, where, let me just kind of draw it up on this first diagram, where this box is going to the left, right? It's going to get pulled to the left with a force of 147.15, and this box is then going to get pulled to the right with a force of 98.1. Okay? So kind of think of the pulley as just changing direction. So sometimes it's easier just to sort of picture them going sideways instead of hanging over the pulley. And because they're tied together, really what we're dealing with is just like the last question. The two boxes are hooked together, so we're actually moving 25 kilograms together, all as one. And we just have those two forces of gravity going in each direction. So the force of gravity of the first box was 147.15. And the force of gravity of the second box was pulling it the other direction at 98.1. And now that we have this simple diagram, it's a lot easier to solve. So our net force will be the one to the left plus the one to the right, so we can add or subtract those. So let's keep our left and right directions as positive, negative. It doesn't really matter which one's which. But let's say we have negative 147.15, and we're going to add on positive 98.1. So that gives us an answer of negative 49.05. So that just means we know it's going to, in the way I've got drawn it here, the net force will be to the left, or in our first diagram, our net force is going to be going downwards, right? The heavier box is going to go down, the lighter box then will go up as a consequence. So we have our net force. Now we can calculate our acceleration just by doing force divided by mass. So we'd have negative 49.05. But we want to use the total mass because they're tied together. And that's the trick to these questions a lot of people forget about. So you want to divide it by 25 because they're working as a system. They're going together as one. So we get an answer of negative 1.962 meters per second squared. So we want to round this to 2 sig digs. So we'll just say it's roughly negative 2.0. Okay, what does the negative mean? Well, our net force was the bigger one, so in this case, our bigger mass, so off our original diagram, it's going to accelerate downwards at negative 2, and our positive one is going upwards, so it'll accelerate the same speed because they're hooked together, but it'll be going at positive 2. And that's it. So we'll stop there, and we'll do a bunch more of these practice type questions with pulleys and things like that over the next day or so.